Welcome back. In this video, we will review what it means to linearize a nonlinear system, how to linearize a LeafSystem in Drake without computing any Jacobians by hand, and use my favorite type of model-based controller, the linear quadratic regulator, to control an inverted pendulum. As always, all the code for this video is on my GitHub page, linked in the video description below. Let's get into it. First, what is linearization? Consider some nonlinear dynamical system with the equilibrium pair x star, u star. What we mean by an equilibrium pair is that if the system state is at x star, the state will remain at x star when the input u star is applied. This could be a pendulum at rest in the down position with no input torque applied. In general, analyzing nonlinear systems and designing nonlinear controllers can be challenging. The tools used in nonlinear control theory are by nature more complicated than that for linear systems. What we'd like to do is apply linear control techniques to our nonlinear system. Thankfully, we have a fundamental result from nonlinear system theory, which states that nonlinear systems behave like linear systems locally. Let's linearize the model about the equilibrium pair and create a linear model in terms of the aerodynamics x dot minus x star dot. Since x star dot is a constant, its derivative is 0. We can perform a Taylor series expansion of the function f about the equilibrium pair to obtain the equation on the right, where the higher order terms are dropped. Since x star and u star are an equilibrium pair, f of x star, u star is 0, and we're left with df dx times the error x minus x star plus df du times the virtual control u minus u star. Of course, df dx and df du are just matrices, so we end up with a linear time-invariant state space model. While we can calculate these Jacobians by hand, we can also use Drake to linearize the system for us and return the matrices A and B. So why is linearization useful? First, it provides a relatively good approximation for most nonlinear systems. The closer to the equilibrium point we are, the better the linear model at estimating the true dynamics. Stability properties of the nonlinear system also carry over to the linear system in most cases. This allows us to design linear feedback controllers using the linearized model rather than considering the full nonlinear system dynamics. Popular controllers from linear system theory are PID, LQR, linear MPC, and others. Of course, to make these controllers, we need to get our hands on the A and B matrices, which we'll now do using Drake. To linearize a LeafSystem in Drake, we need to make our LeafSystem compatible with the AutoDiff class, as Drake needs to take derivatives of the code in the doCalc time derivatives function. The actual code for this has a lot of boilerplate, mostly due to the Python bindings which wrap the C++ templated classes, but you shouldn't get too worried about the syntax. All you have to do is copy and paste the code you see on the screen and then implement your constructor and the doCalc time derivatives function as normal. In fact, I provided a complete working example in the starter code for this tutorial. Once we have our LeafSystem class written, we can linearize. First, we create the pendulum object. Then we specify the equilibrium pair x star, u star. For the pendulum, there are two equilibrium points where u star is 0, the pendulum straight up and the pendulum straight down. We will choose to linearize the pendulum at rest in the down position with 0 input applied by setting the continuous state to x star and fixing the input port to 0. Then we call the linearize function to obtain a linear system. We can use the .a function and the .b function to get our desired matrices. From here, you can create an LQR controller very easily with the linear quadratic regulator function. Now that you have the background, let's actually design our own LQR controller for the pendulum. First, the pendulum dynamic can be expressed as theta double dot equals 1 over ml squared times u minus mgl sine theta minus b theta dot. M is the mass of the pendulum, L is the length of the arm, G is 9.81 meters per second squared, and B is a damping coefficient less than 1. If you want to see how to derive this equation, I have a video in my Lagrangian dynamics series on the screen now. The LQR controller finds a control law which minimizes the integral you see on the screen below, subject to the dynamics x dot equal ax plus bu. If you haven't seen LQR before, it's simple to understand. The term x transpose qx is the penalty for having a state away from 0, while u transpose ru is the penalty for having a large input. By tuning the q and r matrices, you can adjust which states and inputs you want to penalize more or less. It turns out that the optimal control law is given by u equals minus kx, where k is just a constant matrix, which is rather surprising. Even more surprising is that the matrix k is the solution to a well-known matrix equation called the algebraic Riccati equation, which many Python packages can solve extremely quickly. When I'm using LQR controller in my research, I like to start with q and r equal to the identity matrix, and then adjust the diagonal values until I get the results that I want. Again, we just need to get the A and B matrices using the linearize function in Drake, and then we can choose our Q and R matrices. The matrix K is given from the output of the linear quadratic regulator function, and you should play around with different values of Q and R to observe differences in the simulator, just to get a feel for how to tune an LQR controller. The actual control law is again just U equals minus KX. Here's an implementation of an LQR controller in Drake using a LeafSystem. The actual controller is literally just a single line of code. I like to use one file to do the linearization and another for the simulation just to keep my code organized. A pro tip is to save the matrix as a NumPy array, and then your LeafSystem can just read in this value from disk when the simulation is created, so you don't have to manually write the matrix K, which can get very large when you have lots of state variables and inputs. For example, in my PhD research, my K matrix is 4x12, so it's worth spending the time to automate the process. Now let's go into VS Code and view the entire simulation. Here's the code to linearize the pendulum and find our K matrix. So first we're going to define our pendulum class. We're going to use the same boilerplate code from earlier to make sure that autodiff can take a derivative of the system. If I keep scrolling down, we'll go ahead and we'll create a pendulum object. Then we're going to choose the equilibrium point we want to linearize about. If we want to do the up, we do numpy.py, but if we want to do the down state, so we'll set that to 0. Then we can go ahead, do the linearization, and then using our Q and R matrices, we can then calculate K and put it to the screen. So I'll just go ahead and do that real quick. And you see this is our K matrix. We have 0.497 and 1.31. So go ahead and copy these values to the clipboard. Now for the actual simulation. At the top, we're going to define a pendulum class again, but just for clarity, I didn't add all the boilerplate code to make autodiff be able to use this. It's not needed in the actual simulation, but you're welcome to add it. Then I have my LQR controller. The only thing I did here is I pasted the same values for my K matrix. Then if we scroll down, do the actual simulation, we can see what's going on. So first we're going to create our diagram, and then we're going to wire up a plant to the controller and add in some loggers. We'll then set our initial conditions and simulate the system for 10 seconds before plotting the results. Let's run the simulation now. Okay, first you're going to see the diagram. So we have a pendulum plant, we have an LQR controller, and then we have 2 loggers, one for the output of the pendulum and one for the output of the controller. Next, we'll see the angle versus time. This is the pendulum angle, going from 10 degrees down to 0. Now, if we look at the angular velocity, we see that too, going to 0. And then finally, let's look at the input U, and as expected, the controller is doing something. It's actually driving the pendulum to 0 faster than it would go without the controller. And we see that the controller is approaching 0 at 10 seconds. Now let's use an LQR controller to stabilize the system at the vertical equilibrium point. This is where theta is pi, theta dot is 0, and U star is 0. Our LQR control law written in the original state space coordinates is given by U minus U star equals minus K x minus X star. It's important to remember to subtract X star and U star whenever you're stabilizing at a position that is not the origin, otherwise the controller is just not going to work. The only change you need to make to find the new matrix K is to change the state that we linearize the system about from 0 to pi. Remember that you cannot use the previous linearization to design this controller because each linearization is only an approximation of the true system dynamics which are valid locally. Okay, now I'm back in VS Code. Let's just go ahead and get the new linearization about the vertical equilibrium point. So I'm going to set X star to be pi comma 0. Go ahead and run that. And that will give me my new K matrix. So it's going to be 20.1 and 6.32. We're also going to need to update our LQR controller in the simulation. Be sure to update the value of K and also subtract X star in the myOutput function. Now let's go back to the code and make these changes. Okay, I'm back in the simulation. We see that I updated the value of K in my LQR controller. The other thing that I did is I updated this myOutput, as we saw on the slide before. I also went ahead and I changed the initial condition to be 170 degrees instead of 10 degrees. That's just so that we're closer to the vertical when we start the simulation. And so I guess we can just go ahead and run this now. So first of all, we see this response. So we're going to start at 170. It's going to go right to 180. This is a little bit overdamped, so there's really no oscillations going on. We also have our angular velocity looks pretty good, so it's a 0. It goes faster, and then it slows down back to 0. Then our control input. So this also looks really nice. We're going to start at the max torque, and then we're going to kind of go back to 0. So that looks really good. Now just for fun, let's see what happens when we set the initial condition to 0 degrees. So I'll go ahead and do that and run this again. And surprisingly, the LQR controller works. This actually really surprised me because we linearized about the vertical equilibrium point and we started so far away from that, but the LQR controller was able to get us there. So we're starting at the origin, going all the way up. So you'll notice that the angular velocity is really high here. It's over 300 degrees per second. And let's look at the control input. Yeah, control input, 60 Newton meters of torque at the very beginning. That's kind of no good. So while this does work, like if you have some actuator limits, this is not going to actually get you all the way to the top. Just to demonstrate what happens when you do add saturation, I went ahead and made this new file, this task 1C. I went ahead and added the saturation of -5 to 5 between the controller and the plant. And let's just go ahead and see what happens when we simulate. We're going to go from the origin and try to go vertical. So here is the figure. I have the saturation block here between the LQR controller and the pendulum plant. If we go ahead and look at what happens, yeah, it did not get up. So we're starting at 0. It gets up to about 60 degrees, and then it's just not able to get over that hump. So if you loosen the saturation, it will be able to get there, but with our saturation of 5 Newton meters, it just can't get there. So here's the angular velocity. It's a lot smaller. Remember last time we were over 300 degrees per second. Here is our input. So this is not surprising. The input is totally saturated at 5 Newton meters. So you can actually imagine that there are controllers that can get us from the bottom to the top, but this is not the one. So in the next video, I'm going to teach you about a nonlinear control method called energy shaping that we can use to swing the pendulum up even with these extreme saturation limits. The basic idea is to pump energy into the system by swinging the pendulum back and forth until you get close enough to the equilibrium point. If you'd like to give it a shot yourself before the video is up, I've left detailed instructions with plenty of hints on my GitHub page. If you've made it this far, please leave a like below, and if you have any questions or video requests, please leave me a comment. Subscribe so you don't miss the next video in the series. See ya!